This is chapter 4, section 4, optimization. So what is optimization? It's a fancy word for finding the maximum or minimum of a function. And you already know how to do that. So a couple of comments here. We know if you have a continuous function on a closed interval, it has a maximum, it has a minimum at the endpoints or the critical points. So a few examples. Here's a continuous function. The max is at the endpoint, and the min is at a critical point. And we can do another one. Like that. And the min is at an endpoint, and the max is at a critical point. So we know that to find max and mins, we check critical points and endpoints. Now the other theorem we had, if you have a continuous function and it only has one critical point, or one relative max or min, I should say, that will be also the absolute max. So pretty obvious, only one point of relative max or min and is continuous has to be an absolute. And similarly, if you only have one relative minimum and you have a continuous function, no other relative extrema, that point has to be an absolute minimum, not just a relative, but absolute. So that's another way, just checking for one relative extrema of a continuous function, and it's guaranteed to be absolute extrema. Now, in the common thing for optimization problems is you're going to have two equations, and you're going to have to combine the two in order to maximize or minimize what you're trying to do. So we're just do a bunch of examples. So a rancher has 400 feet of fence and is making a corral for his horses. So one side of the corral will be formed by a barn and requires no fence. So we have a big barn. Doot, doot, doot. And then you're going to build a fence out from the barn. The rancher wants 3 rectangular sections within the corral that are perpendicular to the barn. And we also realize that it's going to be a rectangular corral. So we're going to have our fence come out from the corral, but we're going to have 3 sections. So we're going to have more fencing here and more fencing here. So let me change the color of my fence to green, because everyone loves green fencing. So it's important for you to find out what you're trying to maximize. What are we looking for? If you read, we want the maximum enclosed area. So you want to find an equation for area, because that's what you're trying to max. You want max area, therefore you need an area formula. And how do I find the area of this corral? Well, I have to pick variables. It doesn't really matter, I just have to pick something. I'll choose that to be x, and this whole side to be y. So the area is xy. So here lies the problem. If I want to find the maximum, I have to find critical points. But to find the derivative, I don't want 2 variables. So that's what I talked about when you want a second equation to eliminate one of those variables. Now the other key piece of information, you have 400 feet of fence. So where is your fence? You have x there, x there, x there, x there. So the total amount of fence will be 4x plus y, but we know that has a value of 400 because that's how much fencing I have. So you have a choice. Either get rid of the y by solving for y, or get rid of the x by solving for x. And I think it's quite obvious. It's going to be easier solving for y. Subtract 4x from both sides. Now you have an equation with y, or for y. So in place of y, you replace with 400 minus 4x. This is called the restraint variable, or constraint, I should say, because you're constrained to 400 feet of fence. So because of that, you have a secondary equation, and you use that to replace one of your variables. And now, very nicely, we're going to have just one variable, so we can take the derivative. So the area in terms of x will be 400x minus 4x squared. And like we said before, we know max and mins either occur at endpoints or critical points. So we need to find critical points. Critical points are where the derivative is 0 undefined. I take the derivative, I get 400 minus 8x. I set that equal to 0. I add 8x to both sides. I divide both sides by 8. And I get x is 50. Now, my guess would be that's probably dimensions. That's going to give me the max area. But I have to prove it. I can't just assume it. So two ways. And I will show you the two ways. The first is to check all endpoints and all critical points. Before we do that, let's look at x. What's the smallest x could be? Technically, I could make this part of the fence 0. Now that'd be dumb, because it would just be a flat piece of fence against the wall, and there'd be no area. But obviously, x technically could be 0. Now, what's the biggest x could be? If I choose to use no fencing here, no fence, and basically I'm going to have 3 pieces of fence right next to each other. That's dumb again. But theoretically, I could make y 0. I have 400 feet of fence. So if I have 4 pieces, 1, 2, 3, 4, each of them could be 100. That's the maximum value for x. So one way to find max and min is to find, now again, we're trying to maximize area. So we have to find the area at the endpoints and at the critical points. If I plug in 0 into the area formula right here, I get 0. If I plug in 100 here, I also get 0. And if I plug in 50, I get a big number. I actually didn't calculate that. I wish I did. It's going to be 50 times 400 minus 200. I could figure that out. 50 times 200, that's 1,000 square feet. So the question asks the dimensions of the corral. So I found the maximum area, but the dimensions, that means this side would be 50 because we found x is 50, gets you the maximum. But if each of these are 50, that's going to be 100, 150, 200. So all these will take 200 feet of fencing. I have 400, so I can calculate y is 200. So 200 by 50 would be the maximum area. So those would be dimensions, or just plug 50 in here and solve for y, and you would get the 200 similarly. Okay, the other way to find maximum or minimum is to use this theorem. If I only have one relative max or one relative min on a continuous function, that will be the absolute max or min. So I could check for relative min at 50 or relative max at 50. That's x. I want the derivative because that tells me if I have a relative max or min. 20 sounds good, and 75 sounds good. Into the derivative formula, 20 placed there, that's 160. 400 minus 160, definitely positive. Place a 75 here. Ooh, 75 times 8.
The answer is 600.
So 400 minus 600 is clearly negative. So therefore, A has a relative max at x equals 50. Why? Because A prime x changes from positive to negative at x equals 50. And so, since A of x is continuous, and I'm mixing up my handwriting and my printing, and there is only one relative extrema. Therefore, A has a maximum at x equals 50. So that's using the other theorem, saying if you have a continuous function with one relative max, it's an absolute max also. So either one of those techniques can be used for that one. Number 2, suppose that airline policy states that all baggage must be box-shaped with a square base where the sum of the length, width, and height do not exceed 64 inches. Kind of crazy. So here's the base of my box. It's square, and it looks something like that. So the base is square, so I will call that x and that x. And I don't know the length. I'll call it the height here. So let's read what they want. They want the volume, greatest volume actually. So we're trying to maximize the volume. So we need a volume formula, which is x times h, or x squared h. Now we have the same problem. Maximums occur at critical points and endpoints. Well, I have to find critical points, but I have a problem. I have two separate variables. I need to get rid of h, so I need a second equation with h in it. And here's the key, the constraint variables. The sum of the length, width, and height cannot be bigger than 64. So if I want maximum, my length plus my width plus my height cannot be bigger than 64, so I'll make it equal to 64. Now I have a choice, solving for h or solving for x, to plug in here or here. To me, it's easier solving for h. So h will be 14 minus 2x, and I will take that value and replace h with that. And so the whole purpose is to get only one variable in my volume formula. I could have replaced x instead, but it looked easier replacing h. So my volume, I distribute that. It's 14x squared minus 2x cubed. Oh, that's a 64, not a 14. That's pretty bad. So this will be a 64. All right, so I need to find critical points, so I take the derivative, 128x minus 6x squared. I want to set that equal to 0. I'm going to factor out an x and a 2x, I believe. So I'll be left with 64 minus 3x. Set each of these equal to 0. I get x equal to 0. And I do this one also. And x equals 64 over 3. So those are my two critical points. Now, there are two ways. I am going to look at the values that x could be. What's the smallest and what's the biggest? And in the extreme ridiculous case, technically I could make these sides 0, which is lame-o because I have no volume, but technically x could be as small as 0. Now what's the biggest x could be? Suppose I made the height of this box 0. Use none of my 64, which I'm allowed to have, right? 64 inches. I'm going to make h as small as possible. If I make that 0, x is going to be 32. So technically the biggest x could be is 32. So if I look at it this way, I can find the volume at the endpoints and the volume at my critical point. And whichever one's biggest is my maximum, whichever one's smallest is my minimum. If I plug 0 into this equation, I get 0. If I plug 32 into this equation, I get 0. So my maximum will occur, obviously, at 64 over 3. And so, should I do that in my calculator? I should have had this ready for you, but I messed up. So I will hopefully quickly put on my calculator. X squared, 64 minus 2x. I can do this fast. Fast as lightning. Okay, I'm going to find that at 64 thirds. Comes out to be 9,709. This is approximate. 0.04 square inches, I believe. Yeah. So that's the maximum volume, but let's read the question. We want the dimensions of the box. So they didn't ask for maximum volume, but we showed that it occurs when x is 64 thirds. So the dimensions of the box, x would be 64 thirds inches. But what's left for h? So I will look at this formula. That's my constraint formula. H is 64 minus 2 times 64 thirds. 64 minus 128 thirds. Get a common denominator of 3. What's that going to be? 192 minus 128 thirds. I have my handy dandy calculator. That's 64 thirds is h. So h would be also 64 thirds, making it a perfect box. The box with equal sides, a cube. So that's the answer to example number 2. Let's keep going. We're just going to do a lot of these. So let's see what we're trying to maximize. The product of x and y is largest or maximum. So I will call p my function, and it's x times y. But again, I can't solve this because I have two variables, x and y. I need to get a single variable. But they told us x and y satisfy this equation. That is going to be my constraint equation. Should I solve for y or x? To me, I'd rather solve for y. Less work. It's nice and simple. So I will take this value and replace y with that value. So now I have my product is x times 12 minus 3x. I'm trying to maximize the product. Largest possible for the product. So how do you find the maximum? We know maximums occur at critical points and endpoints. So I will take the derivative, set that equal to 0 to find my critical points, add 6x to both sides, divide both sides by 6, and there is my critical point 2. Well, I know this is a continuous function, it's a polynomial. Apparently I have only one relative max or min, so we're going to use that other theorem. If you have a continuous function with one relative extrema, then it's also an absolute extrema. This is my only possible extrema. To find out if it's a relative max or min, I will use the first derivative test. Pick a number left. I'll do 1 and 3 sounds good to me. Plug in 1, 12 minus 6, that's positive. Plug in 3, that's 18. 12 minus 18 is negative. So I'm not going to write this out, but if this were an actual test, I would. P has a relative max at x equals 2 because P prime changes from positive to negative at 2. So we have shown there's a relative max. Then I use my theorem. If a continuous function has only one relative extrema, then it's also an absolute extrema. So therefore, there's an absolute max at 2. And they want x and y. Therefore, x is 2, and y will be 12 minus 3 times 2. Y will be 12 minus 6, or y is 6. There are my x and y's. We just maximize the product of two numbers. We're going to keep going and going. This is the one that will drive you nuts a little bit, so listen carefully as I go through this. Visually, you have a parabola. Looks something like that. I probably should do it in a different color. Blue is nice. There's my parabola. Y equals x squared. Then they tell us we have a point 18, 0. I'll just pick a point out here and call that 18, 0. And what do they want? They are looking for some point P on the curve. So we're looking at some point on this curve that is closest to that. Well, obviously it's going to be there, not here. That's farther away, not here. Somewhere around here, but I don't know where that is. So I'm going to call that point xy because I don't know the coordinates. And the distance between those 2 points is that. I'm going to call that distance d. So we want to minimize the distance. Closest to the point means minimum distance. So I need a formula for the distance. And I claim that that's a distance formula, but you should already know the distance formula is actually Pythagorean theorem. This distance is x minus 18. Now, technically it's 18 minus x, but when you square it, I'll do it correctly because people aren't going to like that. This distance will be 18 minus x, and this distance is y. So Pythagorean theorem is going to say d squared, I will do a different color. One leg squared plus the other leg squared equals the distance squared. So if you square root this, you get the distance. So that would be the square root of y squared plus 18 minus x squared. Okay, taking the derivative of this looks ugly already. And on top of that, I have the problem because I have two different variables. I don't want two variables. So we need another equation, and they told us There's a relationship between y and x. So I'll replace y with x squared. So for here, I'm going to replace it with x squared. And this gets kind of ugly. When you square that, what are we going to get? 18 squared. Let me multiply that out. That's 324. (36x plus x squared). And we can combine like terms and get this. But here's where it gets a little ugly. We don't want to take the derivative of that. That's ugly. So here's my proposal. I call f of x the inside. Here's my logic. If I make this a minimum, small as it can be, so therefore I'm making this inside minimum. Well, if I minimize this, I minimize the distance. So I don't have to minimize the square root of this. I just have to minimize the inside of it, and that will minimize the distance. So that's my logic. So I want to minimize f by finding the critical points. 4x cubed plus 2x minus 36. So I need to take the derivative, factor that. Now, I'm just going to magically tell you what this factors to. Well, first I take a 2 out, and I get 2x cubed plus x minus 18. And then I'm just going to tell you this factors to x minus 2, 2x squared plus 4x plus 9. Okay? And then I set this equal to 0, and you can try it. If you plug this into the quadratic formula, there's no real solution. So I just get x minus 2 equals 0, and I only have one critical point at x equals 2. So apparently, it's when x is 2 and y is 4. So that's what we're going to be looking for. But to prove it completely, I'd have to use that second proof. This one here that says if I have only one relative minimum, that's the only relative extrema of a continuous function, it's the absolute minimum also. So that's the theorem I'm going to use. So how do you do that? Well, we pick points around and see what happens to the derivative. I'll pick 1 and 3. If I put a 1 here and a 1 here, well, that's going to be 2 plus 1 is 3 minus 8. That's negative. Definitely negative. If I plug in a 3, that's 27 times 2 is 54 plus 3 is 57 minus, that's definitely positive. So I'm not going to write this out, but you would need to write this out. Since we go from decreasing to increasing, well, I shouldn't say that. We have a relative min at 2. Why? Because f prime changed from negative to positive at 2. So that would be your claim for relative min. Then you would say this is the only relative extrema of a continuous function. Therefore, it's the absolute minimum of the function. So we can see at x equals 2, we have an absolute minimum for number 4. 2 more examples. So we have a piece of cardboard that's 14 by 10. we want to cut away the corners. So we want to cut little squares off of the corner and then fold up the sides and get a box. Okay? And they want to know what would be the maximum volume of the box. So how big of a square do we cut out? Do we cut out a big square from each corner and make our box? Or a little square from each corner? How big should each of those be? Well, I don't know, so I'm going to call each of these X. They're all going to be the same. We're going to cut the same amount from each corner. And if you see this box, the distance from here to here is the distance from here to here. Those correspond. So let me do that in red. That distance is that distance. Whoa. And how long is that? Well, it's 14. You chop off the two x's, that will be 14 minus 2x. And then this side here for the box, that's that side there. And the total distance we can see is 10, but I chop off two x's, this will be 10 minus 2x. And then the height, well, I'm folding this up. So if I fold these up, the height of the box is x. So I will make that in a beautiful green. Yeah, these are the height of the box. I'm folding these up. So that's going to be x. So what's the volume of this box? It's going to be the three sides multiplied. 14 minus 2x, 10 minus 2x times x. And what am I trying to do? I'm trying to maximize the volume. So I need to find the critical points and the endpoints to get the maximum. Or I can use that other theorem that says if there's only one relative extreme on a continuous function, that's the absolute extreme also. So over here, I'm going to go ahead and distribute there, there, there. So I will do that. That will get me, let's see, 4x squared minus 48x plus 140 times x. So go ahead and just multiply that out and you'll get that. And then we distribute the x. So we get 4x cubed minus 48x squared plus 140x. Now to find the critical points, I take the derivative. So it's the same process we did in chapter 4, section 1, finding critical points and endpoints. I think it's 4.2 actually, to find the relative max and min, or absolute max and min actually. So the derivative 12x squared minus 96x plus 140. I can factor out something, possibly. Actually, what I'm going to do, this doesn't factor. And so you put it into the quadratic formula. There once was a negative boy. Couldn't decide whether to go to radical party. Because he was so square, he didn't go out and missed on 4 awesome cookies. The party was all over at 2A. If you simplify this in a calculator, you get 6.0817 and 1.9183. And you're going to say, man, this has 2 critical points. So I can't use that second theorem. I got to use the first theorem and test critical points and endpoints. So let's look at what x can be. Now, it's kind of silly, but if you cut 0 away, you're going to have a flat sheet, not a box. But technically, you could choose to have 0 height on your box. Okay, what would be the maximum height of your box? Well, from here to here it's 10. Here to here it's 10. Technically, I guess you could chop out 5 and 5 because it's 10 across. So the absolute maximum you could chop off each corner is 5. So that is the endpoints. Now, what's nice about this, that's not a possible, it's impossible. So we only do have one critical point. In this case, I'm just going to find the volume at the critical points and endpoints just to mix it up a little bit here. And these are going to be 0 for these two. If you think about it, it's quite obvious. If you plug this value into this volume formula or this one, you will get 120.164. So it's asking the dimensions of the box. Well, now you know this is the value of x. So I'm not going to calculate these for you, but if you make this x both 1.9183, actually even easier, just plug this value in for this x, that gives you the length. Put this value in for that x, that gives you the width, and then the height is going to be 1.9183. So that's the end of 5. I have one more example. This is crazy. This one's going to be crazy. You're probably not going to like this, but we're just going to do it. We're going to go for it. So you have a movie screen on a wall. So I'll make my movie screen nice and dark, black. It's 20 feet high, the screen. And that screen is 10 feet off the floor. So that's what this 10 feet is, off the floor. Here's your screen. Now, you have to sit somewhere in the theater, so you're going to be sitting here at a distance x away. Now, you want to be at a place where your viewing angle theta is the largest. So you need a formula for theta because you want to maximize theta, so you have to find the critical points and endpoints of that. So how are we going to do this? This one's crazy. Now, I don't expect many people to figure this out, but it's kind of cool using trig. We're going to call this angle down here rho, Greek letter rho. And so you should see two triangles. A golden one here. And I'm going to use this. Can I go no fill? Yeah. We're going to use that golden triangle to get a relationship. So we have the opposite side and the adjacent. So rho, tan rho, is opposite over adjacent. To find the angle rho, though, we arctan both sides. So we have rho. Now we have a bigger triangle here. So we're going to use that big pink triangle to get another relationship. It's going to be tan again, but our angle is going to be theta plus rho. Opposite is going to be 30 and adjacent's x. So opposite is 30 and adjacent's x. To get rid of the tan, we arctan both sides. So theta plus rho is going to be the arctan of 30 over x. Well, we want to solve for theta, so we're going to use this. So we actually are going to have theta plus p, or rho, is arctan of 30 over x. This is going to be craziness, but we know what rho is. It's right there. We're going to place that in for rho, so we only have one variable. Rho is arctan of 10 over x. Well, I'm going to subtract this from both sides, and we're going to get this beautiful formula. For theta. Where do max and mins occur for a function? Critical points and endpoints. So I need to take the derivative to find the critical points. Okay, this is not x, so these are chain rule, it's box. What's the derivative of arctan? It's 1 over 1 minus box squared times the derivative of box. That's actually going to be negative 30 over x squared. You can do the math by rewriting it as 30x to negative 1, move to top. And this, the same thing, what's the derivative of arctan of box? 1 over 1 minus box squared times the derivative of box. When I do the derivative of box, I'm going to get negative 10 over x squared. Simplifying all this, so on top we have negative 30. On the bottom, I'm going to distribute that x squared. So I'm going to get x squared. Here, what's cool, that x squared, they cancel. So on top, I have 30 squared, or 900. On top, I have a negative 10. I distribute the x squared to both of these. I'm going to get x squared. That x squared and that x squared will cancel, leaving 100. And what do we have? Negative 30 over x squared minus 900 plus 10 over x squared minus 100. And I want to set that equal to 0 to find the critical points. Well, I'm going to add this to the opposite side. I'm going to get lazy here, copying and pasting. So I'm going to add this to the other side. So I'm going to, undo that. I want to copy and not cut that. Yeah, so I add this to both sides, you end up with that. Now I'm going to multiply both sides by the common denominator, x squared minus 900 and x squared minus 100 on both sides. Why would I do that? To get these to cancel and these to cancel, and you get 10 x squared minus 900, 30 x squared minus 100. A lot of algebra. That's distribute 10x squared minus 9,000, 30x squared minus 3,000. I'm going to subtract 10x squared from both sides, and I'm going to add 3,000 to both sides. Those cancel, and I end up with 20x squared is negative 6,000. I'm not liking that. I must have made a sign error somewhere, because that's not sounding right to me. Should be positive 6,000. Somewhere a mistake was made, and I'm too tired to find it. It's somewhere. It's there. Somewhere. Hiding. Yeah, I'm just not seeing it right now. Okay, trust me. I made a mistake somewhere. 20x squared. The 9,000, it should have been a plus. Okay, these should have been plus for some reason. Did I mess up early on? Oh, I know where I messed up. Okay, I can fix these. These are plus. That's the derivative. These are plus. That will make everything much better. These are all plus. These are plus. Those are plus. So I'm going to subtract 3,000 instead of adding. So this will be positive 6,000. Okay, here we go. Divide by 20. 300 is x squared. So square root both sides, you get plus or minus radical 300. But you can't do a negative distance. So you ignore the negative. And we're going to get 10 radical 3. All right, so that's going to be my distance. I would still have to prove that that gives me a maximum. But since that is the only critical point, I would have to do, I'm not going to finish this. I'm going to let you do this yourself. So if I do 10 radical 3, I'll do this for you. Let's just get it over with. I want to maximize, so I have to prove that this is a relative max. If it's the only relative extrema, it's an absolute extrema. So easy numbers, 1 in 100. You plug that in, you get plus and minus. If you plug it into the derivative here, plug in 1, plug in 100, you'll get a plus and minus. So therefore, you would justify there's a relative max when x is 10 radical 3 because the derivative changes from positive to negative at that point. Then you would say since that's the only relative extrema of a continuous function, therefore there's an absolute extrema at that point. And that's it for this another long video. Bye-bye.